So, section 5.3, mathematical induction part 2. We really just have one thing to do here, and that's more proofs with induction. Proofs with induction. So the idea here is just to give you some looks at a couple more induction proofs. This first one we're going to do is pretty challenging in that its length is long. But the more you see, the more comfortable hopefully you'll be when you're tackling the homework. And the styles of proof we're doing here in 5.3 are not unique to 5.3. So you can use this in 5.2 and 5.3. Think of this as just more resources, more familiarity. So the first thing we're going to prove is for all integers n, if n is greater than or equal to 0, then 2 to the 2n minus 1 is divisible by 3. Okay, so this is an induction proof, so we need to start our proof by defining our P of n property. So we're going to let P of n be the statement for all n in Z if n is greater than or equal to 0, then 2 to the 2n minus 1 is divisible by 3. So our induction proofs all start out the same. We need to show a base case. So our base case is when n equals 0. So then 2 to the 2 times 0 minus 1 equals 1 minus 1 equals 0. And 0 equals 3 times 0. So 3 divides 0. So we have our base case, no problems there. And we're going to move on to our inductive hypothesis. And that's going to be for all k that are integers, such that k is greater than or equal to 0. P of k is true. P of k being, if k is greater than or equal to 0, then this is divisible by 3 when n is swapped out for k. So now we're going to look at what would happen if we swap in k plus 1. So 2 to the 2 times k plus 1 minus 1. This equals 2 to the 2k plus 2 minus 1, which equals 4 times 2 to the 2k minus 1. So now we're going to do a clever little trick here, and we're actually going to pause this train of reasoning So anytime you have a pause in your proof or you see a pause in your proof, it's almost always going to be signified by a now or a note that or something of that to show that what we're about to write is not connected to this yet. So I like to say, now notice in my proofs that 4 times 2 to the k minus 1 minus 2 to the 2k minus 1 equals 4 times 2 to the 2k minus 2 to the 2k minus 1 plus 1, and this equals 3 times 2 to the 2k. So this is just a justification so that we can say our 4 times 2 to the 2k minus 1 equals 3 times 2 to the 2k plus 2 to the 2k minus 1. So this is some scratch work essentially, but it's vital to the proof to understand why we write it this way. Now, as you go higher in mathematics, your proofs will be more inclined to skip this. I think it's a good idea to show this for our class because we're justifying why we're writing this. But this is true. So you can split off this 4 times 2 to the 2k into 3 and 1 copy, and then your minus 1 sticks around. Well, this is nothing more than our p of k. So we can say, and 2 to the 2k minus 1 is divisible by 3. So there exists some integer t such that we have a multiple of 3. What do we have? 4 times 2 to the 2k minus 1 equals 3 times 2 to the 2k plus 3t. And then we can factor our 3, 2 to the 2k plus t. And since k and t and 2 are all integers, it follows that 2 to the 2k plus t as a whole is an integer. So 2 to the 2 times k plus 1 minus 1 is divisible by 3. And therefore p of k plus 1 is true. P of k plus 1 is true. And by the principle of induction, for n and z, let's put this, for all n and z, n is greater than or equal to 0, then 2 to the 2n minus 1 is divisible by 3. This is a little bit longer one than we've done, but it's a good one, and it also shows you how you can induct on the variable that you want. So this is unlike the inequality type induction proofs that we're used to, or the summation induction proofs that we looked at primarily in 5.2. We're going to do 2 more proofs out of this section, and again they're going to be of this nature where they're not going to be the summation type. Alright, so the next one here, we are going to prove for all integers n, if n is greater than or equal to 3, then 2n plus 1 is less than 2 to the n. So, induction proof, start by defining your p of n. So let p of n be the statement. For all integers n, if n is greater than or equal to 3, then 2n plus 1 is less than 2 to the n. So our base case here is not 0 or 1. They've clearly defined our base case needs to be 3. So 2 times 3 plus 1, is 7, and this is certainly less than 2 to the third, which equals 8. 7 is less than 8, absolutely. Okay, moving on to our inductive hypothesis now. Hypothesis. That's how you spell hypothesis. So we're going to assume P of k is true, and that is for all k that are integers, if k is greater than or equal to 3, then 2k plus 1 is less than 2 to the k. So we're going to look at what happens when we swap in k plus 1 now. So we have 2 times k plus 1, and this equals 2k plus 1 plus 2. So 2 times 1 is 2, and I'm just rewriting the order. And I'm doing that because, just as we talked about in 5.2, I need that p of k to appear. And we have it right there, 2k plus 1. So this is certainly less than, come on, papers, work for me. 2k plus 1 plus 2 is certainly less than 2 to the k plus 2. And since k is strictly larger than 3, or it's at least 3, 2 to the k plus 2 is less than 2 to the k times 2. K's are getting small here, sorry. So we can kind of break this down. Since this is at minimum 8, if it were 1, if we allowed k to be 1, this inequality would fail. Because if k was 1, then this would be 2 plus 2 is less than 2 times 2. And we know that's false. So since k is strictly 3 or bigger, we know that 8 plus 2 is always going to be less than 8 times 2. And it all hinges on this, that change in our domain. And this is 2 to the k plus 1. So 2k, 2 times k plus 1 is now less than 2 to the k plus 1, which is what we wanted. And that was our goal. So we can say by the principle of induction, for all n that are an integer, if n is greater than or equal to 3, then 2n plus 1 is less than 2 to the n. And that's the end of our proof. So this is a good example of making sure you're thinking about all of your pieces, not just your inductive hypothesis. But a lot of times, if you have a domain that's not start at 1 or start at 0, it's for a very specific reason. And usually that reason is to make the statement true. So keep that in mind as you're working through homework problems. If you're seeing k values or starting values, n values, that don't begin at 1, that say start at 2 or 3 or 5 for some reason, know that that's important. And you're going to most likely be using that in conjunction with your inductive hypothesis. So you're going to assume your inductive hypothesis, work through that logic for the k plus 1 case, and then need your restricted domain to justify a certain step. In this case, like I said earlier, this proof fails because this inequality is not true if we start at 1, for example. So we start here, and that's what gives us the whole proof. All right. So let's try one last one here. This will be a nice short section for you all. So we are going to let a sub k, the sequence, be defined by its general term a sub k equals 5a sub k minus 1. And this is for all k greater than or equal to 2 and a sub 1 equaling 2. So we have a recursively defined sequence. We're starting our k's at 2. They give us our first term. And they would like us to prove for all n greater than 0 that that a sub n equals 2 times 5 to the n minus 1. So you did this in Calc 2. You took a recursively defined sequence or series and you found its unrecursive version. We'll start our proof like we always do, identifying what our P of n is. So let P of n be the statement. For all n greater than 0, this was supposed to be a that here. That a sub n equals 2 times 5 to the n minus 1. Given a sub k equals 5 a sub k minus 1 for all k greater than or equal to 2 and a sub 1 equaling 2. Right, so we want to make sure we have all of our information in the body of our proof. So our base case, we have to be greater than 0, so that means our base case is going to be 1. So let n equal 1. And so now we're going to use the fact that we know a sub 1 is 2 and hope that our new definition for the general term matches. So a sub 1 equals 2 times 5 to the 1 minus 1, which equals 2. Great. That's what we wanted. So then our inductive hypothesis will be to assume P of k is true. That is, for all k greater than 0, a sub k I should probably not use k, right? Let's change to m. Let's make this m, and I'll just rewrite this. A sub m equals 2 times 5 to the m minus 1, only because we already have the k's up there, so don't want to get confused. So this is m and m. So now we look at our, in this case, m plus 1 case. So a sub m plus 1 would be since we can't assume that this is true, we're actually doing a sub m plus 1 using this. So this would be 5 times a sub m plus 1 minus 1, which is 5 a sub m. Now there's our inductive hypothesis hiding away. So this then equals 5 times 2 times 5 to the m minus 1, which of course is going to equal 2 times 5 to the m. And let's go to the next sheet here. So if we have 2 times 5 to the m, we can write this as 2 times 5 to the m plus 1 minus 1. And now we have our result. That's what we wanted. Now the trick here and the thing that we have to make sure we understand is that when you start your am plus 1, you can't plug it into this because this is p of m plus 1. So you have to plug it into the original recursive definition and show that you can turn it into the form that we desired, our new definition, 2 times 5 to the m minus 1. But that's what we wanted. So by mathematical induction, or the principle of induction, for all n greater than 0, a sub n equals 2 times 5 to the n minus 1, given a sub k equals 5 a sub k minus 1 for all k greater than or equal to 2. And a sub 1 equals 2. And that's our proof. Now there is a little thing that I'd like you to read in the book. If I'm not mistaken, there is a homework problem that asks you to think about it. I'm not sure if there's a proof, but it's page 265, and it's on trominos. So we know what dominoes are. Trominos are 3-sided dominoes, essentially, with 3 groups groupings of pips. Okay, that's the end of 5.3.